Today we're going to be doing lesson 7.1.2, which is sampling distributions, lesson 2. So, exploring simulated distributions of sample proportions. In the previous lesson, we learned about sampling distributions of sample proportions. We learned that the mean of a sampling distribution of sample proportions is equal to the population proportion. What that means is when you take samples from a population, we expect that the average of all of the samples you take will be the real proportion. That makes sense, right? We did some demonstrations last time. We also learned that the variability of sample proportions depends on sample size. Sample proportions from larger samples tend to be closer to the population proportion than sample proportions from smaller samples. In this lesson, we use simulations to examine how the spread and shape of distributions of sample proportions are affected by sample size. This will prepare us for the type of thinking that is involved in statistical inference. So let's look at a problem regarding global warming. Okay. The Gallup organization conducts surveys in many countries to obtain categorical and quantitative information about how people feel about important issues. One important topic that Gallup investigates is people's views about climate change. Gallup surveyed people in the United States during March 2014 and found that 16% of Republicans worry a great deal about global warming. For this activity, let's assume that Gallup's result, 0.16, is the population proportion of all Republicans who worry a great deal about global warming. What this sentence means is that we're going to assume that the Gallup result of 0.16 is the true answer. In other words, we're going to assume that 16% of all Republicans that exist worry a great deal about global warming. We will use computer simulation to explore what happens if we repeatedly select random samples of various sizes. Download and open the central limit theorem simulation at the web link. So I have already loaded that Excel file. That is what we see here on the right side. And that's what we're going to be using for this discussion. Let's begin by simulating samples of size n equals 20. And again, we're going to put p equal 0.16 and we're going to do n equals 20. So I'm going to change some values here. So here where it says p, it says 0.500. I'm going to change that to say 0.16. There we go. And my n is going to be 20. So this is what it looks like. We're going to leave the observed sample proportion as 1. Okay, so this, I don't know if you could tell, but this is actually blue right here. Everything underneath the curve is blue. So what are we looking at here? The computer simulates 1,000 random samples from a population in which 16% of people worry a great deal about global warming. From each sample, a sample proportion is computed and plotted on a dot plot. So I want to remind you guys of what we're looking at here. So let me explain. Let's say that, so n is 20. What that means is, let's suppose that you got a sample of 20 random Republicans. Okay, 20 people. And then you found out how many of them are concerned about global warming. Whatever the answer that you get, let's say that 20% of them are, then you put a dot right here at 0.2. And then you do it again with a different random sample of 20 Republicans. So what you're looking at here is 1,000 samples. This is why there's so many dots here. There's actually 1,000 dots there. To give you an idea, to get you a stack that gets this high up, there's almost 250 of those, see? So that's 250 dots, or a little bit less than that. Here's maybe 225 dots and so on. So you could see what the results are here. Okay. Okay. So the computer simulates 1,000 random samples from a population in which 16% of people worry a great deal about global warming. From each sample, a sample proportion is computed and plotted on a dot plot. Behind the dot plot, a normal curve is graphed to model the distribution of sample proportions. The entire curve may not be visible because sample proportions only range from 0 to 1. Remember, the complete normal curve is bell-shaped and symmetric and extends endlessly in both directions. So you could see here that we do see a bell curve that roughly matches the dots, right? We see that it doesn't match it exactly, but you could see that it is approximately bell-shaped, although it is cut off right here because of the 0 that we hit, right? We can't get less than 0 Republicans that believe in global warming in a sample, so that's why it gets cut off right there. So let's answer the following questions. Let's describe the center, shape, and spread of the distribution of sample proportions. So first, let's look at the center. What would be the center? It wants us to estimate the mean of the distribution. Okay, so what would be the center? Well, looking at this picture here, the center appears to be right at 0.16, right? We notice this bell curve. It appears to be at 0.16. So I'm going to put some text in here. And I'm going to add some text right in here. So I'm going to say the center is about 0.16. Okay. Let's look at the next part. The next part asks us for the shape. It says, describe the shape. Is it normal with symmetric tails or is it skewed? Well, if we look at this, because of the fact that it cuts off right here, we would say that this is more or less right skewed, isn't it? Because it doesn't finish on the left side. So I'm going to say that it is roughly bell-shaped, but cuts off, so it is right skewed. What about the spread here? It says, what is the standard deviation of the sample proportions? So we can notice right here, it says the sample standard deviation is 0.081. So I'll say the standard deviation of the sample proportions is 0.081. Okay. All right, so let's keep going here. We are going to continue on. It says this collection of sample proportions is part of the sampling distribution of all sample proportions from samples of size n equals 20. Okay. Now, why is it not all of them? Because notice it says it's part of. The reason that it's not all of them is because we only did it 1,000 times. All of them would be if we did it forever and ever and ever. Okay, you would get a smooth shaded thing. You wouldn't get these things that don't go all the way and everything, right? Okay, so it says below are 4 dot plots of sample proportions similar to the computer simulation. The dot plots are for sample sizes of 20, 40, 70, and 100. Each dot represents up to 4 data points. Match each dot plot to its correct sample size and think about how the sample size affects the spread of the sampling distribution. So what did we learn in the last lesson? Remember, we learned that the bigger the sample size is, the narrower our normal distribution, right? So let's look at these pictures. Here we have something that goes from 0 to 0.45, right? That's a pretty big spread. And as we go down, we notice that this is a little bit narrower. So dot plot 2 is narrower. Dot plot 3 is even narrower. And then dot plot 4 is the most narrow one of all. So it looks like, since they're getting narrower with each time, if we want to do a matching thing here, it looks like this is the sample size of 20. And it looks like dot plot 2 would be the sample size of, let's see, 20, 40, 70, and 100. It looks like they're getting bigger as we go down. So this would be 40. The next one would be 70. And then the last one would be the 100. Okay. So let's go on here. It says, think about how the distributions of sample proportions change in the dot plots above as the sample size increases from 20 to 40, 70, and 100. Okay? Sample proportions are used to estimate population proportions. Unfortunately, sample proportions typically contain error. How does the sample size tend to affect such error? Well, it seems like as we increase the sample size, the error decreases, doesn't it? Because each dot gets closer and closer to the mean, right? The mean doesn't change. What's changing is how far away the dots are from it on average. So let's write that down. As the sample size increases, the error tends to decrease. Okay. Next question. Does the distribution get wider or narrower with larger sample sizes? Well, we know that it gets narrower, right? The distribution gets narrower with larger sample sizes. We learned that the standard deviation of a statistic is called its standard error. What happens to the standard error of the distribution of sample proportions as the sample size increases? Well, because it gets narrower, that means that the standard deviation decreases, right? In other words, the standard error decreases. So as we increase the sample size, the standard error decreases. Normal distributions are symmetric and bell-shaped with the mean at the center. Does the distribution of sample proportions become more or less normal as the sample size increases? And explain how the 4 dot plots above support your answer. Let's look back at all of these pictures, okay? You notice that as we begin here with a sample size of 20, we notice that it sort of looks bell-shaped, but the problem is the fact that it's really spread out, and also it seems to be right skewed here because of the left cutoff here. So notice that this is somewhat normal, but it's not super normal. And this simulation on the right shows the same thing. But notice as our sample size got bigger and bigger, here's a sample size of 40. It's starting to look more like a bell curve. Sample size of 70 looks even more like a bell curve. And then sample size of 100 looks even more like a bell curve. So what does that mean? This means that as the sample size increases, so, okay, let me put this here. As the sample size increases, the distribution of sample proportions becomes more normal. Okay. This is a really, really important fact, okay? This is saying that as our sample size gets bigger and bigger, everything looks more and more normal. And normal is a good thing because it means we can use our calculator to do computations. You may wonder, well, does that mean we need huge samples? No, we do not need huge samples, but it does need to be big enough. And in this section, we are going to learn what big enough actually means. Okay? So for number 4, we're going to need a calculator. Recall from the beginning of the lesson that 16% of Republicans worry a great deal about global warming. Recall also that the mean of the sampling distribution of sample proportions is the population proportion P, and that the standard error is given by that formula. Remember, we've got this standard error formula here, which is the square root of P times 1 minus P over N. What we're going to do is we're going to use that formula to calculate the standard error ourselves. And then for the next one, we're actually going to look at the computer simulation and see if we get a similar answer. So it says determine the mean and standard error for the sample size of n equals 100. Okay, so let's go first with the mean. Remember, the mean is always equal to the population proportion. And so that means that the mean is just 0.16. Now, what about the standard error? That we're going to need the formula for. So we've got this formula right here. So what are we going to do? We're going to do the square root of P times 1 minus P over N. So that's going to be 0.16 times 1 minus 0.16 divided by the sample size is 100. So we're going to put that in our calculator. So let's see what we get using our actual calculator. I'm going to do second, and then the square root symbol. And then I'm going to do 0.16, parentheses, 1 minus 0.16, close parentheses, and then divided by 100. When I hit enter on this, I end up with 0.037, right? I rounded up because the 6 rounds to a 7. Again, that's because the next number after it is a 6. So 0.037. So I'm going to put that right here. 0.037. So these are our two values. We got for mean and we got for standard error. Remember, the mean is always the same as P, but the standard error changes according to the sample size. We're going to look at number 5 now, and this does require the simulation, so I've pulled it back up. In the central limit theorem simulation, change the sample size to n equals 100 and redo the simulation. How do the values that we computed in question 4 compare to the mean and standard error of the simulated proportions in the simulation? So again, let's recall, these are the values that we calculated that should be the theoretical perfect values. But now we're going to do a simulation. So what we're going to do is we're going to take a sample size of 100. This is equivalent to taking 100 random Republicans and asking them, and then doing that 1,000 times. So let's see what happens. Looks like this. So let's see what we get. Notice up here in this box, it says the mean of sample proportions is 0.159. 0.159. And then the standard deviations right here, or the standard error, is 0.036. How do these compare to what we have up here? Look at these two values and then look at these two values. They're almost the same, aren't they? So the values are almost identical to the theoretical values from question 4. Why are they not exactly the same? Well, remember, we didn't do this an infinite number of times. We just did it 1,000 times. But the more times we do it, in theory, these two numbers should approach exactly these two. And that's pretty believable because look at how close these values were. Okay, so let's move on. The central limit theorem for sample proportions. It turns out that sampling distributions of sample proportions become more normal as the sample size increases. Recall from the previous lesson that a sampling distribution of sample proportions is the distribution of all possible sample proportions from samples of a given size. In other words, every possible sample you can take. In the last example, it would have been every possible sample of 20 Republicans, right? Which is a lot of samples, right? Every possible one. If the sample size is large enough, this distribution is going to be approximately normal. So that's what we're about to learn now. We want to learn how big that has to be. Statisticians have learned that sampling distributions of sample proportions are approximately normal whenever n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. Since p is the proportion of successes and n is the sample size, n times p is the expected or the mean number of successes in a sample of size n. That is, on average, samples of size n will have n times p successes. So remember, if p is the proportion of successes, then if you subtract it from 1, that's the proportion of failures. So n times 1 minus p is the expected number of failures. So the important part here that I'm going to highlight is the criteria for normality. So the sampling distribution is approximately normal if it meets the criteria for normality, which mean that there are at least 10 expected successes and 10 expected failures. Before I read on, let me try to break this down for you. This means that you need to choose your samples large enough so that you expect at least 10 successes and at least 10 failures in your sample. So let's read the following part. As an example, recall that in the previous lesson we were sampling 50 M&M candies and assuming that 24% of all M&Ms are blue. What would be the expected number of successes in a sample? It would be n times p. So there's 50 M&Ms and you multiply it by 0.24 and this gives us 12. And that just means that out of 50 M&Ms, we expect 12 of them to be blue. So how many failures do we expect? Well, you do n times 1 minus p, that gives you 38. In other words, in 50 M&Ms, we expect 12 blues and 38 of them to not be blue. Okay? Of course, the number of blue M&Ms varies in individual samples, but since both of these numbers are at least 10, the normal distribution is a good approximation for the sampling distribution of sample proportions. In other words, sample of size 50 is big enough with the M&M example. Okay, so let's look at the next part, and this is the important part. This is again, you need to know. This means this is extremely important here. So let's read this together. It says you need to know the central limit theorem for sample proportions. A sampling distribution of sample proportions from a population with proportion p is approximately normal if, and again, here's the criteria, right? N times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. So that's what has to be true first. If that's not true, then that means your sample is not big enough, okay? And you cannot apply this next part. But if they are both 10, then we could say the following. the mean, mu sub p hat, and the standard error, which is sigma sub p hat, of a sampling distribution of sample proportions are, and this is them, right? The mean is just equal to p, and the standard error is equal to that formula, square root of p times 1 minus p divided by n, where p is the population proportion and n is the sample size. Let's go on. Representing a sampling distribution with a normal distribution. When a sampling distribution of sample proportions satisfies the normality criteria of n times p greater than or equal to 10 and n times 1 minus p greater than or equal to 10, we can use the normal distribution properties to find probabilities or percentages corresponding to sample proportions. This is something that we did in the last class. You guys learned how to use your calculator to find probabilities under a normal curve. And I'm going to remind you of how to do that in these next problems, okay? Let's start by doing number 6. Consider the proportion of Republicans who worry a great deal about global warming. 16%, or p equals 0.16, that was reported in the Gallup survey above. Okay, so remember, we're taking this as fact. We want to think about how the shape of the distribution of sample proportions helps us identify the likelihoods of various ranges of outcomes. In one random sample of 120 Republicans, 24 responded that they worry a great deal about global warming. So let's answer these questions. The first question asks us, what is the sample proportion p hat? Remember, p hat is going to equal, in our sample, the number of successes divided by the total size of the sample. In this case, a success would be the people that worry about global warming in the sample, and the sample size would be 120 Republicans, right? And so it would be 24 divided by 120. What would that be? So if we use our calculator and we do 24 divided by 120, I get 0.2. So p hat is, let me write it with the 0 there, 0.2. So that's p hat. You'll notice, by the way, that p is 0.16. We don't expect our p hat to match p exactly, right? That's the whole point. The samples are always a little bit different. So let's see if this sample size is big enough. Is the normality criteria met? Well, let's go ahead and figure out what n times p is. So remember, n is 120. So we have 120 times p, so that's times 0.16. So if I do 120 times 0.16 in my calculator, I get, and I recommend that you do these along with me with your calculator to make sure that you get the same answer as me. I get 19.2. And now we're going to do n times 1 minus p. So I'm going to do 120 times 1 minus 0.16. Okay, don't forget to put the parentheses in your calculator. So when I multiply those two things, I get 100.8. So we're not done here because this is asking us if the normality criteria is met. Remember, what's the normality criteria? Let's go back up to here. The normality criteria is that both of those have to be bigger than 10. So what do we think? Is 19.2 bigger than 10? Yes. It's greater than or equal to 10. 100.8 is also greater than or equal to 10. So this means the normality criteria is met. Okay. the normality criteria is met. What does that mean? That means that we can now use the central limit theorem. So this means that I can do the next part. What would the mean be? Remember, the mean is just p. So that's going to be 0.16. What's the standard error going to be? We need to use that square root formula, right? So I'm going to do the square root of p times 1 minus p. So that's going to be 0.16 times 1 minus 0.16 divided by, in this problem, the sample size is 120, right? So I'm going to do that in my calculator. I'm not going to demonstrate the calculator presses this time because I already did that in this video. So it's the exact same thing. So when I put it in my calculator, I get 0.033. Please put it in your calculator. Make sure you get the same thing. It tells us to use 3 decimal places here, and so I'm going to do that. I'm going to write 0.033. So that would be the mean and the standard error. And again, we can only do that because we have normality. Normality is met. Now, again, what does it mean to have normality? It means that we actually get a bell curve. Okay? So here is our bell curve. And we're going to fill this in. Let's read this. It says the boxes under the normal distribution below are 1 standard error apart, with the center box at the mean. Use the mean and standard error above to enter the correct values into the boxes. So what I'm going to do is I'm going to rewrite these here so that we know what to put. So we know that the mean, again, is 0.16, and we know that the standard error is 0.033. So we now need to fill in this box. And so I'm hoping that you guys remember this from the last class, okay, Math 21A. Remember that the middle of a normal distribution is always the mean. So I'm going to start by filling in this guy is 0.16. How do I get the next guy? So remember, if this is the mean, I get this next guy by doing the mean plus 1 standard deviation. And then I get the next guy by doing the mean plus 2 standard deviations. And then I get the next guy by doing the mean plus 3 standard deviations. So what I'm going to do is use my calculator, and I'm just going to keep adding 0.033 to it. And again, please do it along with me, okay? So let's do that one to the right. If I do 0.16 and I add it to 0.033, I end up with 0.193. I'm going to take that number and add 0.033 again. I get 0.226. Sorry about that. There we go. 0.226. And then if I add 0.033 again to that, I get 0.259. What about going the other way? Remember, when we go to the left, we actually have to subtract, right? So this guy would be mu minus sigma. Here would be mu minus 2 sigma. And here would be mu minus 3 sigma. So if we subtract, we get 0.16 minus 0.033. We end up with 0.127. And then if we subtract 0.033 again, we get 0.094. And then if we subtract 0.033 again, we get 0.061. I'm hoping you guys got the same numbers as I did. The next part, we're going to have to remember something from Math 21A. It says use the empirical rule to determine the interval that contains 95% of the sample proportions in the sampling distribution. Okay, so I want to remind you guys of the empirical rule. The empirical rule says that we have 68, 95, and 99.7. So the empirical rule says that if you want one standard deviation in either direction, that's contained by 68% of the data, and two standard deviations is going to be 95% of the data, and then three standard deviations is going to be 99.7% of the data. So because they want 95%, we actually want two standard deviations, right? So what would that be? Well, that means we're going from two standard deviations to the left until two standard deviations to the right. So this would be our 95%. So what are we going from then? The interval goes from 0.094 until 0.226. What does this mean? This means that 95% of the time, the samples are going to sit between those two numbers. In other words, that's how close on average, not on average, sorry, but that's 95% of the time, if you were to take a sample of that size, 120 Republicans, the percent of them that's going to care about global warming is going to be between 9.4% and 22.6%. Which makes sense, right? Because the real value is 16%. So we're saying that that's how close we're going to get most of the time. Okay, plot the sample proportion from question 6a as p hat on the graph above. Is this value unusually large? Okay, so let's look at 6a again. What did we get? So remember, we got a sample of 0.2, right? The question is, we know that that's large, right? Because the real value is 16% and we got 20% here. I don't want you guys to be confused because 0.2 is the same as 20%, right? So 0.20, 0.2, same thing. So we know that's large. The question is that unusual? So let's go to our picture and plot where that goes. 0.20. So where does that go in our picture? So I'm going to put it in with, let's use red here. 0.20 sits between 0.193 and 0.226. So I'm going to say that it's probably somewhere like right there. So this is p hat. So question, is that unusually large? How did we decide if things were unusually large in Math 21A? Remember, things are unusually large if they are more than two standard deviations above the mean. So is this value unusually large? Well, two standard deviations would be this number right here. This is two standard deviations above the mean. And so since our p hat is not bigger than that, that means that particular p hat was not unusually large, right? Anything bigger than 0.226 would be unusually large. Okay, so let's go ahead and let's write that down. No, p hat, which is 0.2, is not unusually large. Sorry about that. Is not unusually large since it is less, or let me write it this way, since it is within 2 standard deviations of the mean. Number 7 now. In the central limit theorem simulation, set p equal to 0.16, n equal to 120, and particular sample proportion equal to your answer from question 6a above. Okay, so let's go ahead and do that. We're going to do those one at a time here. So let's start with p equal to 0.16. It's already there. N equal to 120, so I'm going to change that n to 120. And then the particular sample proportion, that's going to be, so what I'm going to do here is put 0.20 here because that's the answer that we got for 6a. So I'm going to put 0.20. Hit enter. What does this look like? So you notice that what it did is it shaded the red part above 0.20. Okay, so what it did is it's shading all of the proportions that are greater than that. So let's look at part A. It says the simulation gives the relative frequency of sample proportions that are greater than or equal to the sample proportion p hat observed above. What is that value? Okay. So if we look here, relative frequency of sample proportions that are greater than or equal to 0.2, it tells us that 0.139 is the answer. So let's write that down. Okay. So remember, this is number 7. 0.139 is the relative frequency of sample proportions greater than or equal to 0.20. Okay, so now let's look at the next part here. It says with n equal 120 and p equal to 0.16, the sampling distribution of sample proportions is approximately normal. What is the area to the right of the observed sample proportion under the normal curve? So that's given in this box right here. The area to the right is 0.142. So 0.142 is the area to the right of 0.20. So how do those the next part asks us, how does this value compare to the relative frequency? So I'm hoping that we notice that 0.139 and 0.142 are very similar to one another. So they are nearly equal to each other. So what is the point of this? The point is that the area to the right, this is the exact answer, and the relative frequency is, so let me put it this way. The area to the right is the theoretical answer, and the relative frequency means that in this simulation, that's the proportion of them that were above that. Okay? What this means, another way to think about it, is this is the proportion of samples that gave us more than 20%. Okay? So put another way, if you take 120 Republicans and sample them, then only 20% of the time you're going to get a sample, or sorry, only 14% of the time, right? 0.14. Only 14% of the time you're going to get a sample where 20% of them or more think that global warming is a big deal. So this last problem is going to require some calculator usage, but this first part is pretty basic, so let's go ahead and start there. Remember that when gathering random samples, many outcomes are possible. But if the conditions for approximate normality are satisfied, we can analyze them with the normal curve. The whole point here, guys, is that once you have a normal distribution, we can use our graphing calculators to tell us a lot of interesting information. So let's go ahead and try this problem. It says, for example, suppose that we do another random sample of 120 Republicans, and it contains 11 people that worry a great deal about global warming. What is the value of this new sample proportion? And let's round it to 3 decimal places. So there were 11 Republicans out of 120, so I'm going to write 11 divided by 120. And we're going to round that to 3 decimal places. So if I do 11 divided by 120 in my calculator, I end up with 0.092. Okay, that's me rounding to 3 decimal places, okay? What is the z-score of this sample proportion? Remember, z-scores are, you can get a z-score by actually subtracting the mean from the value that you got and dividing it by the standard deviation. Okay, so we need to get this from question 6C. So let's recall what we got in question 6C. So if I come up here to 6C, remember we had a mean of 0.16 and we had a standard error of 0.033. Okay? So let's write that down. We know that the mean is 0.16, and we know the standard error is equal to 0.033. What is the z-score? Let's recall this is actually something that you guys learned how to do back in Math 21A, so this should be a refresher here. But in order to find a z-score, the formula is that we need to take our value and subtract the mean and divide it by the standard deviation, okay? So what do we end up with? Well, let me actually back up here because some other symbols that you might see, I might actually write it this way. P hat minus the mean divided by the standard deviation. So that's just going to be our p hat is, sorry about that, our p hat is 0, oh wait, let me scroll up a little, there it is, 0.092, and we're going to subtract 0.16, and then we're going to divide it by 0.033. So this last part is going to have some heavy calculator usage, so I want to demonstrate with the calculator. Part B isn't so difficult, but Part C is definitely going to use more calculator stuff. So let's go ahead and finish up Part B. We want to do 0.092 minus 0.16 divided by 0.033. So let's do that in our calculator. I'm going to do the parentheses first, open that up. And then I'm going to have 0.092 minus 0.16. We're going to close the parentheses up. It looks like that. And then I'm going to do divided by. And then I'm going to do 0.033 or 0.033. So if I do that and I hit enter, I get my answer. I get negative 2.06 if we round it to 2 decimal places, okay? Negative 2.06. So let's go ahead and write that in here. So this next question asks us, or actually it's a part B of that question. It says, does this z-score indicate that the sample proportion is unusually low? I'm a little out of space here, so I'm going to put my answer here as a continuation. And I'm going to say, what do you guys think? Is that value unusually low? Remember what a z-score tells you. It tells us how many standard deviations above or below the mean something is. So let me remind you guys just a general rule. This is from Math 21A. If z is bigger than 2, then that means it's unusually large. And if z is smaller than -2, then that means it's unusually small. So what do we have in this case? Well, -2.06 certainly satisfies this, right? So I'm going to put a circle around this. We have an unusually small value. In other words, let's think back what this problem is asking here. That means that it is unusually small to only get 11 Republicans out of 120, right? Because look at that, that's 9.2%, and we know that the real answer was 0.16, so 16%. So this is a very low answer, and in fact, it's so low that it is unusual. So that's part B. I'm going to answer part C below here. Part C says, use technology or a normal distribution table to find the probability of observing a sample proportion that is less than or equal to the value from question 8b. Okay, so what are we trying to do here? What we want to do is we want to find the probability that our value, our z, is less than or equal to -2.06. How do we actually do that? Well, this is using a calculator function. And the way that we do this is we're going to do normal CDF in our calculator. So I drew a little normal curve here, and just so we can get an idea here, if this is 0, this is our z-scores, right? If this is 0, then this is -1, and this is -2. What we're saying is we want to figure out what proportion of that picture is shaded to the left, which is going to be a very tiny number, okay? Okay, so how do we actually do this? This, as a reminder, this is where we use the normal CDF function on our calculator. So I'm going to write this down. This is normal CDF. And I need to put the lower limit and the upper limit, okay? So normal CDF, you start by doing the lower limit, and then you do the upper limit. So what would our lower limit be here? Well, aren't we shading to the left forever here? So when we're shading to the left forever, then that means that the lower limit would be -1e99. -1e99. And the upper limit is going to be, well, how far to the right do we go? We only go up to -2.09, right? -2.09. And so I'm going to put that here, -2.09. So how do we actually find this answer? To find this, we need to use our trusty TI-84 calculator. So here's my TI-84. From the beginning, this is what you're going to do. We're going to go to distribution. You guys see that button right there? Above it, it's DISTR. The way we reach that is by hitting second and then distribution. And we're going to go to normal CDF. On my calculator, it's the second one down. You hit enter. Your calculator should ask you for the lower limit and the upper limit, okay? So the lower limit we know is, I'm going to hit delete here. The lower limit is, I'm going to do -1. The E is above the comma, that EE right there. So I'm going to do second and then EE and then 99. And this is what it looks like after you put it in. Now this value is going to be -2.09. Go back down to here and you hit paste. Now this is what we get. Okay, it says normal CDF and it has all this stuff here. Now if your calculator is one of the older ones, it might just go straight to the screen and then you have to put in those two things yourself. Either way, you have to type in -1E99, comma, -2.09. But all we do now is hit enter. What do we get? We get 0.018. 0.018. So I'm going to put that right here. This is our answer. Just to finish this up, I want to talk about what that means. That means the chances of getting a sample that is as small as that is only 1.8%. Okay, 0.018 is the same as 1.8%. Okay, so I just wanted to put down both answers here so that you guys understand they are the same thing. You just move the decimal place over 2 times. Okay, but that is how you use the normal CDF on your calculator, and we're going to be doing that quite a bit in this class. Okay. And I believe that is it for this video. So thank you so much for watching. And just to give you guys the code word for this is Gallup. This is the code word. Code word is Gallup. Thank you very much for watching, guys.